All right. So we just have next week, and then we finally have our winter break, or our not winter, or fall break, right? Right, that's gonna be nice, yeah. I'm sure a lot of you are really looking forward to it. All right, so first things first, I should have finished grading all the exams. Y'all made it really easy for me, which is generally either a very good thing or a very bad thing. But in this case, it was a very good thing. The average score was an 87. I think the lowest scores was in the 60s. So, and so just a heads up on this. I did not alter your, so remember the group portion cannot hurt your grade. So if your group portion score, your percentage on the, the percentage score on your group portion is lower than your, your solo score, it will be raised after I go through it. I just wanted to let you see what your scores were on the solo and on the group section before I went and fixed the grade on the group section. So you can see what both you scored and what your group scored. In most cases, like, I think the lowest group score was like an 84 or something along that line, 84, 83. It was a low 80, low mid 80. So, which is good. So overall, overall, people think that the group format was pretty good for that. Great. Unfortunately, the final is not going to be that way. So, final is just the normal final exam, but I will be, at least for 2168, I plan on keeping this forward so long as the labs land on the same day, because you're able to do your exams in lab. Didn't really work out for 1051, I feel. But for this class, I feel like it works well, especially since I'm already yelling at y'all to collaborate with each other. If you have any questions on to how I graded your score, please let me know. It is quite possible, I misclicked or something when grading. Yesterday was a bit hectic. I had to, I was doing a lot of grading yesterday. Then it turned out late. I had a late night emergency, or a friend had a late night emergency that I then went and, basically made sure that somebody was at their house while they were at the hospital. So, watch your kids. They're fine. Everything's fine. But long story short, that meant I was grading at like 9, 10 o'clock, 9, 10 o'clock. So, it's quite possible that late at night I made a mistake, or something. So if you have any questions, again, let me know. Now, before we go into our work section, I wanted to talk a bit about that sorting algorithm I teased on Tuesday, called Radix sort. Okay. So Radix sort is, as I mentioned, a sorting algorithm that does not deal with comparisons at all. It's a sorting algorithm that's basically made to say, if I can't compare these things, how in the world am I supposed to sort them? And the way it works is that it categorizes things. It sorts by categorizing rather than comparing. So it requires you to know kind of something about what you're sorting. So for instance, knowing that you're sorting in a decimal system or a binary system, or you're alphabetizing, right? Here, what happens is that we basically put the cards in, and the cards then get sorted into one of 13 output baskets. So don't know why they have 13, but the point being is that this is an an automated thing. And I mentioned this works with queues, and it has a really weird runtime, which is OW comma times N. Now W, while it will be, it's kind of a constant, but it's one of those we can't really ignore because of how specific it is. And I'll demonstrate that why. It's like, you'll see the runtime and you're like, why don't we use this for everything? Because it's often, because unless we're dealing with billions of items for integers, it's not worth it. So I'm going to demonstrate this by sorting, by doing like by doing, let's say 4-digit numbers. Sorry, 3-digit numbers. So 798. Let's do 124, 876, 008, 425, and 091. So I'm prepend. So notice that for anything that's not a 3-digit number, I'm prepending zeros just for ease of use. And now what I'm going to do below is, now that I've got the 6 numbers I'm going to plan on sorting, I'm going to create a queue. I'm going to create, actually not a queue. I'm going to create 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 queues. 1 for each digit. One for each digit. And now the way this sorting algorithm works is that we sort everything by throwing everything into the appropriate queue based on its least significant digit. Okay, so in other words, we're going to go through this. The least significant digit, in other words, the one place for 798 is the 8 queue. So it's going to go over here into the 8 queue. Right? 124 is going to go into the 4 queue. 876 is going to go into this queue. 008 is going to go into this queue. Let the top of the queue be the front of the queue. Okay, let the top of the number be the front of the queue. So 008, 425. And then 091. So that's our first round. We're going to do 1 round for each digit. Okay. Now what we do is erase the entire stroke. Boom. That's so useful. Okay. So now what we do is that we put every number into the queue, and now we dequeue everything in order from 0 to 9. So 0 has nothing to dequeue. So we're going to go and dequeue 091, then 124, and then 425, and then 890, and then 876, and then 798, and then 008. And this is one of the things when you think about it, it's going to be a, oh, of course that works kind of deal. So notice that everything, since we put it into queues and then we dequeued based in the order of the queues, that everything kind of in the order that we would expect, that it's ordered by least significant digit, right? 91, 124, 425, 876, 798, and then 8. Everything is in order by the least significant digit, which is something. So we're going to do this again. But we're going to go for the next least significant digit, which means that we are going to do the tens place, right? Now for strings, what we'd be doing is that we'd be, sorting by, like you'd be sorting by the first letter, and then you'd be putting everything into queues based off of that. Would it be the first letter? No, you'd be sorting by the last letter, and then sorting everything by that, right? And then do the second to last letter, and it'd be queues that are labeled A to C. But here we're going to do the tens place. So here, this will go into the 9 queue because it is 091. We're doing the tens now. 124 will go here. 425 goes here. 425. 876. 798. 798. And then 008 goes over here. So now notice for the 2 queue that 124 and 425, they're in order because the last digits were already put in order. And so now when we DQ, we get 008, 124, 125, sorry, 425, 876, 091, 798. So everything's in order based on the least significant, the two least significant digits, right? If these were just 2-digit numbers, you know, and we were to truncate off that hundreds place, everything would be sorted now, right? Because we sorted by the ones, then we sorted by the tens. Now we're going to sort by the hundreds. So 008, 124, 425, 876, 091, and then 798. And we can see fairly trivially that now that we DQ everything, we get 008, 091, 124, 425, 798, 876. There we go, it's in order. So first off, this requires as many iterations as you have digits, okay? So in this case, we have 3 digits, it's gonna require 3 iterations. That is our W, that is the word size. Okay, so this took 3n time, right? Took 3n time, we had 3 iterations through this loop. And technically it was, you know, 3 to put in. We put it in the queues 3 times and then we moved it out of the queues 3 times, but honestly, that's a trivial operation, right? So W is the N is the number of keys and W is the key length. Now, why don't we really use this? Well, let's think about this for a second. If we were sorting binary numbers, integers in Java and in C are 32-bit integers, right? Which means that, and they're in binary, which means that we have the following 2 queues, 0 and 1. And since they're 32 digits long, that means that the runtime is around 32n. Okay. Now, our most optimal algorithms are as follows. They are n log n. So the question is, you know, this as n increases, when is this the better choice? When n is really, really big, we need log n to be equal to 32 for this to be for this to kind of matter, which means that when we really want to use, if we're going to even consider using it, because there's, you know, it's a radically different algorithm. Plus, you know, we've got this memory cost here as well to store things in our queues. We would need n to be equal to 30, you know, to 2 to the 32 at that point. We'd have to be sorting about 4 billion items. And then it's not nearly as optimized as other sorting algorithms are. But you don't have to do any comparisons. And it can be automated with a system like this, right? You don't even need a computer to do it. You can just build a machine that the way it looks at those values is that it uses punch card values. You know, so it's a pretty cool, implementation. Yeah, Bragg sources are most commonly applied to binary strings and integers. It's been shown that some batch markers can be faster than more general purpose sorting algorithms, sometimes 50% to 3 times faster. So I wrote a faster sorting algorithm. Is Radix sort quicker? So there is, looking at doing that, but I mean, if it ever becomes faster, you'll see it be implemented as a go-to algorithm, in Java, in like Java and Python. Java uses 2 sorting algorithms. It uses quicksort and merge sort built when you're doing sorting built in. Sorry, quicksort and timsort. It uses quicksort to sort any array of primitives. Why because quicksort is extremely efficient. It uses a dual pivot implementation of quicksort, meaning it's going to be using 2 pivots rather than the one that you learn. So it's extremely efficient. And it's memory efficient too, which is really nice. But for objects, it uses timsort because it needs the sorting algorithm to be stable, which means that when I try to sort if I'm trying to sort an array like this, let me just annotate here. If I'm trying to sort something like this, 7 to A, 5 to B, 4, my output in a stable sorting algorithm needs to be 2A, 2B, 4, 5, 7, where A means it was the first in the input, and B was the second in the input. So in other words, the first 2 in the in the input is the first 2 in our output. This only really matter, but 2s are 2s, so this doesn't really matter for this case. But for objects, this can matter because, just because objects have same values may not mean that they're the same item, and you may not want to mix them up. So we use a stable sorting algorithm for that case. So again, on the exam, what I care about is insertion sort, quicksort, and merge sort for the final exam. Okay, and don't worry, I plan on spending plenty of time. I plan on spending the lectures once we get back from winter break, from fall break, reviewing that final exam. Okay, so, all right. So with that, I will, let you get to demoing or your questions.
Date time for the final?
What?
Do you have a date and time for the final?
The school does. Give me a second. I'll figure that out. Yes. So I don't try to figure it out because I worry if I write it down, then I might forget to change it one semester, and then it's going to be a mess. I figure out the final time and date the same way everybody else does, which is, here we go, share screen again. Temple academic calendar, 2022, 2023, right? Where is the final exam calendar? Academic calendar over here. Come on. They never make it.
It's down there.
Final exam schedule. There we go. Okay. Click on this document. This is the document we use and the document I use, right? Also, it's worthwhile mentioning this clause. This is just simply to give some leeway in case stuff doesn't work out, but you're not supposed to take more than 2 finals in a day. If you're scheduled to take more than 2 finals in a day, please go and speak to one of the deans. If one of the professors isn't moving, because if you have 3 finals in a day, that's too much. Obvious, just talk to a professor, tell them to arrange for you to take it at a different time. If none of them budge, go to a dean and escalate. Okay, it's your right as a student to not take more than 2. Obviously, if I'm one of the 3 professors, I'm more than willing to move and accommodate your schedule. Okay, last I checked. Let's see. Do we have, is it this time around? Okay, nope. There we go. So I write the final for everybody, but we meet during this thing. So day class meeting, I believe we use the 3 hours because we're 3 lecture hours and 1 lab hour. Okay. So you won't find our time over here on the 4 credit, even though it's a 4 credit course, right? You see, it's not here. So here it is, Tuesday, Thursday. So it's 12/13, which means that our last day of classes is the 5th. Yep. And again, as it gets closer to the final, I will send out announcements, so you'll be able to find it. So this is the typical time when I see it. It is both a great time and a horrible time. It's great because you got plenty of time to prepare for it. It's horrible because you won't, because it's the last one and you're going to have spent most of your energy preparing for the other ones. Okay, that is actually the biggest difficulty that students have with the final, which is that you're already kind of mentally exhausted and just ready to be done by the time you get to it. Okay, that is the hardest part about the final. Okay, but it will be from 10:30 to 12:30. It will be here. Okay, in this classroom. It will be in this classroom here. We are mildly it will be electronic. We are mildly limited on power sockets. So 1, be sure that you charge your laptop. 2, if you don't have a laptop or your laptop can't be charged that much before you come for some reason, I will make sure that I have some paper backups, so print identical exam, print it out so that you can write down in case there's technical difficulties. And there's always laptops from the kiosk downstairs. Yes.
Battery packs.
Oh, yeah.
From the library, plug into that.
Yeah. Yeah. Although once you get here, you probably don't want to waste time running to there. That's why I have the paper, because you'll be able to work on that. And honestly, the exam I give electronically is cut down from the version I give on paper, because again, coding on a laptop takes slower than coding on paper. All right. Yes. So Nathaniel, I see your hand up.
Yeah, I just have one little issue with my code for the Queen's problem. I'm like so close.
Okay. All right. So
I was trying to go over it with the